Okay, thank you. Well, like I was saying, this is a very special moment for me. I'm so happy to be the chairman of this of Next Talk, because our next speaker, Richard Aron, he was my PhD advisor at Kent State. I did the PhD with him, Kent State, on some three nonlinear problems. And so I really, that was when I started growing as a mathematician. I really have very good memories from my stay there in Kent State. And so I'm really extremely and deeply thankful to him for all he taught me, like all the mathematics I know, like everything I learned from him. So it's really a pleasure to introduce him now. So he's going to be speaking about some problems of possible. I'm sure there will be a lot of interest. Thank you very much.
Well, thank you. Can you hear me? Thank you. Well, it's an honor. It's an honor to be here. Can you hear me now? Now can you hear me? Okay. If it gets too boring, okay. So I mean, the talk. At the moment, the key word is possible. So let me explain what I'm talking about. Okay, so I'm going to give two rather, obviously short presentations. And let me make a graph. Time is 0 to 30, but it won't be 30, but it'll be less than 30, but 0 to 30. And this is interest. Your interest. Okay? Now, what I hope is, and as I say, it's going to be two possible parts. So maybe here, and I hope we begin like this. And then I say the first part is going to be a little bit more technical. The second is not at all. So I hope that the second part, it will be like this. That's my hope. But sometimes I'm disappointed. So it could be like this. And at the end, you will all hate me. So, well, let's see. So, okay, and as I say, the first part is going to be more, slightly more technical, but not too much. Each part has two definitions, so here we go. So the two definitions are about what we call WMP, where to go, WMP, and CPP. So what's the WMP? So a pair XY, one of spaces, has the weak maximizing property, means the following. You take any operator from X to Y, and suppose that you can have a sequence Xn in the ball, such that T of Xn approaches the norm of T, and moreover, Xn itself does not converge weakly to 0. And then if that happens, then T attains the norm. And whenever that occurs, we have this weak maximizing property. Here's another property which doesn't seem to be related. It's the compact perturbation property, CPP. And this is much easier to understand. If I have two operators, T, K from X to Y, K is compact. And suppose that we have this inequality. then T plus K attains the norm. So in other words, if the perturbation by compact increases the norm, then you have attaining the norm. Let's do an example. So the example is the scalar field. Let's T be 0. Let's let K be any continuous linear form. So let's say that we have CPP, compact perturbation property. So what does that mean? T is 0, so there instead of T is 0. And K is some linear form, and it implies that K attains the norm. So any linear form attains the norm. So what it means is we have reflexive. Now, okay, I mean, and I don't remember what year, but not so many years ago, Domingo Garcia, Daniel Pellegrino, and Eduardo Teixeira, the two are from Brazil. Domingo's from Valencia, and I. And what we showed was that the weak maximizing property implies the compact perturbation property. So I'll just go. So the weak maximizing property is this slightly technical thing, and the compact perturbation property. Now, what I'll do is, I don't know about the time, but what I'll do, the smartest thing to do is this. I'll recall what a famous American president from the 1960s and 1970s said. I won't give you the proof, you just have to trust me. So let me go very quickly. And no, well, yeah, let me just see. The summary, WMP implies, I mean, and you can see that's really the proof, so it's not very long. WMP implies compact perturbation property, that's what we showed. If y equals k CPP, compact perturbation implies reflexive. That was just a remark we made before. So, okay. By the way, suppose X is reflexive. If X is reflexive, automatically you have, and so if X is reflexive and Y is the scalars, then automatically you have weak maximizing property. The reason is, you take an operator which is a linear, now it's an operator into K, into scalars, so it's a linear form. And it attains the norm because it's reflexive. Therefore, it attains the norm at some non-zero vector. Take that vector and repeat it infinitely often. That's a sequence which works, it's non-zero, it attains the norm there. Okay. Now, here are questions which we wondered about, and there are many questions still around. This is fairly recent material. So we wondered about the converse, whether reflexivity implies weak maximizing property in general. And in 2021, Sheldon Dantas Mingujong from Korea and Gonzalo Martinez from, I think, Granada, I'm not sure, show that for some non-reflexive monospace pair, CPP does not imply weak maximizing property. So even what we wanted is by no means true. So, okay. Then later, it was observed a few years ago, there are no examples of reflexive spaces which give counterexamples. They're still open. And they also show, though, take a reflexive monospace, you can find another reflexive monospace Y, and you can find two operators, T and R. T is an operator, and Y and R is rank 1, so it's as simple as it can be, which have the following property. The norm of T is less than the norm of T plus R, so we have this perturbation by rank 1 operator, but T plus R is not normative. So there are many things which are somehow delicate, subtle, and, well, Well, I hope at this point, well, now the second part of the talk. So, and again, this is, I mean, well, this began in the 1990s or 1990s. But let me begin with two definitions. So X is an infinite dimensional vector space, and this is somehow vague. P is a property, and the property is something that some vectors in the vector space may have it, and some vectors may not have it. And S of P is those which do have the property. So it's a subset, maybe empty, but not so interesting, but it's a subset of the space of this Banach space, infinite dimensional vector space. And P is said to be linearable if this set contains an infinite dimensional subspace. And I should say S of P, we add 0 to it, the 0 vector, because sometimes, well, just to avoid trivialities. And it's called, P is called spaceable. I should say that if you use any kind of editor when you're typing, spaceable occurs in red because the word doesn't exist, except that's how life is, and nor does lineable, but in any case, if moreover S of P contains a closed infinite dimensional space. Okay, these concepts were known to Vladimir Gurary in the 90s, and they were extended quite a bit by many mathematicians, many of them Spanish mathematicians, Paquito, Manuel Maestre, Juan Sewanli, and many others, and other, not only Spanish people, but. Okay, let me give you some historic examples. So, the property, I mean, in each case, I think it's obvious what the property P, where to go, P is. So here, in the first example, the property is nowhere differentiable. Okay. So look at the collection of continuous functions in the closed interval 0, 1. And I mean, it's spaceable. Namely, you can find a closed infinite dimensional subspace. And in fact, okay, this was a result of Vladimir von Gurary and Kadets. The Kadets, the father, not the present nowadays son. And it was improved substantially by Luis Rodriguez Piazza from Sevilla. Okay, so, and this somehow is typical, this example is somehow typical of what's going on. Namely, the function, the property is an unpleasant one, let's say, not very nice. How about the corresponding nice property? Namely, the set of everywhere differentiable functions. What can you say about that? Well, it's lineable, it's a vector space. You can take two everywhere differentiable functions and add them and everything is fine. It contains the polynomials, so it's an infinite dimensional space. But in fact, Gurary showed it is not spaceable. There are no closed infinite dimensional spaces. And what I want to do is just give examples. So the rest of the talk is really going to be just some examples. Okay, so E is for everywhere surjective. So these are functions from R to R, so from the reals to the reals, such that, no, I mean, I have the board, so I'll use it. You take any interval, there's a function such that on any interval, the range is infinite, any interval. So take a smaller interval, there. So it's, I would say, surprising, at least at first glance, that such a function exists. And I can tell you I know two proofs, and one is surprisingly, well, it's direct. It's not, it doesn't use any machinery at all. Anyway. And what's surprising is that it is, oops, sorry. It contains a vector space of enormous cardinality. So, maybe not intuitive, but that's how life is sometimes. Okay, now this is not hard to explain, but there are too many indices, so I'll do it very quickly. We're going to look at three numbers. So it's it's D and K. D is going to stand for degree of polynomial, and K is going to describe size, number of dimensions. And given D and K, there is another integer m, such that the following occurs. Take any polynomial in m variables, complex polynomial in m variables, then it will be a constant on the polynomial is of degree D or less. It will be constant on a subspace of dimension K. Okay, now this is a result actually that was solved the problem in the Scottish book at the end, more or less, of the 1990s. And just to give you an idea, not of any particular interest, but if you have, what it shows is that if you have a polynomial in quadratic, a degree 2 polynomial in 25 variables is constant on the subspace of degree 11. What you do with that information, I don't know, but it's an example. Okay, and it's going to be, in fact, originally it's a proof about an infinite dimensional space. And there are some positive and negative results about zeros of polynomials, and let me just skip them, except to say that there's a paper I have with Chris Boyd, Ray Ryan from Ireland, and Ignacio Zalduendo from Buenos Aires. And we're very proud. The paper appeared in the Journal of Approximation Theory, I think, I'm not sure. And we're very proud of the title of the paper. The title of the paper is Zeros of Polynomials, the Real Story. And why the real story is because we're interested in real. Now, if you think about it, it's completely trivial. You can't have the results in general. Take the polynomial summation xn squared. So, okay, there's nothing, it's going to be 0 on where it's going to be 0 is nowhere except the origin. But for cubics, it's already interesting. And I won't go into that. Okay, so here are some strange examples of functions. So the property is that it's everywhere differentiable, but nowhere monotone. So again, I have the blackboard behind me, but I can't draw it anyway. So, okay, there is such a function. Here's a result of Chiselsky and Juan Seoane. And from 5 years ago, there's a function from R to R such that for any large subset of S of R, the function restricted to S is not continuous. Now, so the function discontinuous on S. A little over 100 years ago, it was shown by Bloomberg that no matter what function you have from R to R, there's a function there's a set which is dense and on which the function is continuous. So, okay. Here's a result of Mazurkiewicz from the 1930s. Again, not somehow anti-intuitive, I think. Namely, there's a function from 0, 1, a continuous function on the closed interval, which takes sets of measure 0 to sets of measure 0. But if you translate the function by anything which is not 0, it no longer does that. So again, these are strange, anti-intuitive examples. Here's the theorem. Each of these properties not only exists, I mean, your intuition, my intuition is that you look at that and there should be no such function at all. And in fact, there's an infinite dimensional subspace of such functions. So let me give, and you know, I'm almost at the end, maybe of your patience, but I'm also at the end of my time, and it's the following. Let me give examples where lineability fails. So there's a result of Gurari and Quarta from 2004. Quarta is actually a very brilliant mathematician who saw the future and now is making a lot of money in banking. But in any case, he look at the real valued continuous functions on 0, 1, which attain the maximum, not the supremum, the maximum at one point and only one point. Okay? Now, this set is a density delta. It's very easy, the set of such functions. To this, you can see I have to add the zero function because the 0 function does not attain its maximum at only one point. So it's a density delta, but any vector space contained in it has dimension at most 1. So here's another example. This is maybe the most famous example in recent times by a Czech mathematician named Martin Remutil from 2017. NA, so X is a Banach space. NA of X stands for norm-attaining functionals. So NA of X are the phi in X star such that phi attains its norm. And the question is how, well, we know from the theorem of Bishop-Phelps, let's see if I wrote that. Yeah, if X is reflexive, then of course everything attains its norm. So NA of X is exactly all of X star. The Bishop-Phelps theorem says that NA of X is always a dense set in X star. And Remutil's result is you can renorm C0, the null sequences, to get that it does not contain a two-dimensional subspace. So again, lineability fails spectacularly. This is really an ongoing area. And when I say ongoing, on Friday, today is Monday, on Friday I got an email from Miguel Martin strengthening this result. So, I mean, work continues. Now, I should mention a result of Daniel and Paquito from their youth, which is that every infinite dimensional Banach space admits an equivalent norm such that the norm attaining is lineable. And what I don't know, but maybe I bet Paco or Daniel know, is whether there's a same kind of result where NA of X is not lineable. And I don't know that, but maybe they do. Okay, so I really want to finish with just a couple of questions. And I mean, let's imagine somehow a real life situation. You're walking home last night from the Casa Balbino, and you meet somebody on the street from Sanlúcar, and he asks you, he gives you a set, and he asks you, is this property from this set is it a lineable property? Happens all the time, I'm sure. But what happens? How do you guess? I don't have any intuition. In each case, property, and I don't have a feeling about how even, what I do know is that there are very many papers which show lineability, that you do have subspaces. There are very few which are, but that doesn't prove anything, but that there are very few where and thank you very much.
Thank you very much for the amazing talk. Are there any questions, remarks, Professor Simeon? Any other questions or remarks? Okay, I'll just I was just looking at the questions that you posed before, like in 2008, I found an example of, this is just an example, not a renorming, of a non-reflexive Banach space. It's actually a quasi-reflexive Banach space in such a way that the non-normative functionals is not even too lineable. And as and actually I was thinking of probably renorming a space, non-reflexive spaces in such a way that they could have some property related to like quasi-reflexivity, or at least that the space is a maximal subspace of its bidual. So in such a way, then you get not even true lineability of the non-normative function. But the question, renorming non-reflexive Banach spaces for which the set of non-normative functionals is not lineable. That's still, I believe, is still open.
Yeah, and I should say the example, I don't know what you would have, but it's C0, null sequencing, and it's the renorming, equivalent norm of C0. And the work that they do.
Oh, the microphones. Oh.
But now I have to say something more significant. The work with C0 originally, fundamental work was done by somebody called Charles Reed. And it's extremely complicated. Well, to me, it's extremely complicated.
It is complicated.
And the examples the work that follows really use Reed's work. So other techniques would be welcome.
Definitely. Any other questions or remark? Okay, so let's thank our speaker again.